Hey everyone, I'm Rowan McKee and welcome to From Zero to Zeta, where we explore mathematics from the ground up. This is Math Wikipedia Roulette, a lighter side series where I let Wikipedia decide what math we talk about next. Here's how it works. We start on one math-related page. Today we're beginning right where it all starts, 0. And I'll follow a few links from there to see how far down the mathematical rabbit hole we can get. I'll keep things quick, intuitive, and a little chaotic because that's half the fun. At the end of each episode, I'll narrow down a few of the pages we could visit next, and you get to decide which we follow next. You can cast your vote in the YouTube poll linked in the video description. Whichever page wins becomes our next stop in the series. So if you like exploring math in an unexpected direction, hit like, subscribe, and help guide where we go next. Alright, let's spin the wheel and start from 0. Okay, we are starting from 0, true to the name of the channel. We're gonna explore where this takes us in the first episode of the Math Wiki Roulette. The first thing I always want to look at is actually not the math itself, but the history of it, where it came from. That makes me want to look actually at the etymology section. So we have the word zero came into the English language, French zero from the Italian zero, contraction of the Venetian zeviro, form of Italian zefiro. That's the etymology. Now we get into the history. What's interesting is that 0 didn't always exist as a symbol. It originally, the way people represented 0 was literally to leave it out, like a space. The lack of a positional value or 0 was indicated by a space. This was actually fairly common up until relatively recent times. Even the Greeks had no symbol for 0. The story I heard is that it eventually became a dot, and then a little circle, and then the circle just grew until it became the symbol we know today. I don't know if that's actually true. We will find that out. The Mesoamerican long count calendar used base 20 instead of base 60 or base 12. And the ancient Greeks had no symbol for 0. According to mathematician Charles Seif, the ancient Greeks did begin to adopt the Babylonian placeholder 0 for their work in astronomy after 500, representing it with the lowercase Greek letter omicron. However, after using the Babylonian placeholder 0 for astronomical calculations, it would typically convert the numbers back into Greek numerals, which didn't have zeros. They seem to have a philosophical opposition to using 0 as a number, which makes sense because 0 represents nothing, right? It represents nothing. The natural way to represent it is to not represent, because it represents nothing. Greeks were famous for their philosophy, right? Even the mathematicians of their time were philosophers first, and then mathematicians. Some of them asked, how can not being be? How can we represent the absence of something with something? There is a cognitive dissonance there that doesn't work philosophically. Yeah, and China also used an empty space denoting 0. 0 as a number, as a symbol, didn't come into common usage until much later. You can almost call it the newest of the numbers, if that's a thing. And it looks like the oldest surviving Chinese mathematical text using a round symbol for 0 wasn't until 1247. That's like over 1,000 years later. So in the 7th century, we had a description of division by 0. A positive or negative number when divided by 0 is a fraction with 0 as denominator. 0 divided by negative or positive number is either 0 or is expressed as a fraction with 0 as numerator, and the finite quantity as denominator. 0 divided by 0 is 0, which is false, and says incorrectly describes division by 0. It makes sense that one could come to that conclusion. In the 12th century, someone proposed that division by 0 results in an infinite quantity, which is closer to the truth, actually. A quantity divided by 0 becomes a fraction, the denominator of which is 0. This fraction is termed an infinite quantity. In this quantity consisting of that which has 0 for its divisor, there is no alteration, but many may be inserted or extracted, as no change takes place in the infinite and immutable God when worlds are created or destroyed, though numerous orders of beings are absorbed or put. The proposition that division by 0 results in an infinite quantity makes sense because as you decrease the denominator in a fraction, the result tends towards infinity. You can actually make a number system where division by zero is defined. It results in this kind of behavior. So this is where the word algorithm comes from. Algoritmi de numero indorum, from Latin in the 12th century. There's a connection to Fibonacci here, which you may have heard of the Fibonacci numbers after this guy. One thing that immediately comes to mind when I think of the number zero is that it's the additive identity. So it has a very clear connection to algebra right there. It's the additive identity because adding anything to zero doesn't change the outcome. It has a bunch of connections to other areas of math too, of course. Because we use zero, mathematicians don't always mean the number zero when we write the symbol for zero. We often mean whatever the additive identity of the set is. And sometimes what we're working with isn't even an algebraic structure in that way. It just behaves like some additive identity in some context. So, for example, in set theory, zero is the cardinality of the empty set. Zero is often used to denote a false value. So zero doesn't even have to represent a number. It can represent a true or false value. And in category theory, there's the idea of a zero object, often denoted by the number zero. And the related concept of zeromorphism generalizes as a zero function. A zero object would be anything that maps to itself for every connection. And a zeromorphism, actually, I don't know what a zeromorphism would be. I guess a zeromorphism might just be it maps all to one. That would be a constant morphism, not a zeromorphism. Let's see. Category theory, branch of mathematics. Zeromorphism is a special kind of morphism, exhibiting properties like the morphisms to and from a zero object. A zero object. A zero object is an initial object. That's something we could click on. Kind of interested to see how it connects to category theory in that way. And of course, it's got a bunch of connections to other fields. Computer science, zero plays a role in array indexing. Oh, interesting. I didn't actually know this. In the BC calendar era, the year 1 BC is the first year before AD 1. There is not a year 0. In astronomical year numbering, the year 1 BC is numbered 0, the year 2 BC is numbered -1, and so forth. I think we're going to click on zeromorphism. Alright. Category theory, branch of mathematics. A zeromorphism is a special kind of morphism exhibiting properties like the morphisms to and from a zero object, which we have already seen is the same as an initial object. An initial object is something in category theory that basically doesn't have any morphisms, any functions from anywhere else. It just goes to everything. Okay, so we got a category, and F goes from X to Y is a morphism in C. Morphism F is called a constant morphism, sometimes left zero morphism. If for any object W in C and any GH W to X, Fg equals F8. Dually, F is called a co-constant morphism. I see. So I was pretty close to them. What I was thinking of what might be a zeromorphism being a constant morphism. It turns out there's actually two different kinds of constant morphism. A zeromorphism is one that is constant and co-constant, which just means that it absorbs from either direction. In the category of groups, a zeromorphism is a homomorphism maps all of G to the identity element of H. Yeah, that makes sense. And then a constant morphism would just map all of the elements to one element in H, but not necessarily the identity element. Okay, but this is probably starting to get a little bit abstract. Let's see if we can find something a little bit lighter. But we're also trying to get as far away from zero as possible. You could click on the empty set. You could click on category of sets. I don't know what is best here. I feel like the empty set is pretty close to zero, so we probably want to go with the category of sets. Okay, but now we're still in category theory, but we're talking about sets. That's just a set is just a collection of objects. Now we have a category, which is just a set of objects and functions going between those objects. So it's literally dots and arrows, and the objects are sets. Composition of functions is associative, and the empty set is the initial object in the set. The reason why this is the case is that nothing can map to the empty set. You're basically saying, give me a value, and I will not return anything. But a function has to return something. There is no function that goes to the empty set. There are functions that you don't give anything into, and they'll return something. They're not very useful, but they exist as functions in this setting. You can think of like a zero argument function returning just some constant. Like, I don't know, if we made pi a function, but there's no argument. We're not putting anything into it. It just returns 3.14 every time. This is the kind of thing that exists from the empty set to other sets, and why it's called an initial object, because nothing goes to it, just from. We have a reference to ZF set theory. That is different from ZFC. So Zermelo-Fraenkel set theory is set theory, but without the axiom of choice. You can learn more about it here. What is the axiom of foundation? The axiom of regularity is an axiom of ZF set theory. It states that every non-empty set A contains an element that is disjoint from A. In first order logic, okay, I don't know what a Grothendieck universe is. Set U with the following properties. If X is an element of U, if Y is an element of X, then Y is also an element of U. If X and Y are both elements of U, then X, Y. Set which is itself a model of ZFC, for instance, if a set belongs to a universe, its elements in its power set will belong to the universe. The existence of Grothendieck universes, other than the empty set and the set VW of all hereditarily finite sets. What is that? Hereditarily finite sets are defined as finite sets whose elements are all hereditarily finite. In other words, the set itself is finite, and all of its elements are finite sets, recursively all the way down to the empties. It is not implied by the usual ZF axiom. It is an additional independent axiom, roughly equivalent to the existence of strongly inaccessible cardinal. Cardinal numbers is strongly inaccessible cardinal. It is uncountable, regular, and a strong limit cardinal. Whatever that is. Cardinal is a weakly inaccessible cardinal if it is uncountable, regular, and a weak limit cardinal. I don't know what that means. I have no idea what that means. That's wild. Okay. Actually, we started from 0. 0 is pretty concrete. Thinking this strongly inaccessible cardinal deal seems like the best way forward. What is a strong limit cardinal? Limit cardinals are certain cardinal numbers. Cardinal number lambda is a weak limit cardinal if lambda is neither a successor cardinal nor 0. This means that one cannot reach lambda from another cardinal by repeated successor operations. We're talking like infinite limits here. So a cardinal number is like 1, 2, 3. But if it's a limit cardinal, then no matter how many times you add 1, will never get to that cardinal. So we're talking about infinite numbers, basically. Since about 1950, inaccessible cardinal has typically meant strongly inaccessible cardinal, whereas before it meant weakly. Weakly inaccessible cardinals were introduced by Hausdorff. Strongly inaccessible cardinals were introduced by Sierpinski and Tarski and Zermelo. In the latter, they were referred to along with Aleph 0. So Aleph 0 is the cardinality of the integers. It represents an infinite quantity. And the reason why this is important is that we actually get different sizes of infinity between the integers, the real numbers, and then sets of functions. So it becomes useful to have representation of these cardinalities, even though they're all infinite in some fashion. Aleph 0, I guess, would be an example of a strongly inaccessible cardinal, but it represents countability. Not actually sure. Oh, the generalized continuum hypothesis that all weakly inaccessible, strongly inaccessible as well. I know what the continuum hypothesis. So the continuum hypothesis states that there are no cardinalities between Aleph 0 and Aleph 1, between Aleph 1 and Aleph 2, etc. Let's look at a couple of examples. So two notions of an inaccessible cardinal kappa describe a cardinality kappa which cannot be obtained as a cardinality of a result of typical set theoretic operations involving only sets of cardinality less than kappa. Hence the word inaccessible. By mandating that inaccessible cardinals are uncountable, they turn out to be very large. Particular inaccessible cardinals need not exist at all. That is, it is believed that there are models of ZF set theory, even with the axiom of choice, called ZFC, for which no inaccessible cardinals exist. A large cardinal property is a certain kind of property of transfinite cardinal numbers. These transfinite cardinal numbers are what I was talking about, like you cannot reach them through normal addition. An ordinal is a weakly inaccessible cardinal if and only if it is a regular ordinal and it is a limit of regular ordinal. So 0 and 1 are regular ordinal, and this omega is what I was referring to when I was talking about like transfinite numbers or things that you can't access just by adding repeatedly. And I would think it would be at least weakly inaccessible cardinal, but I guess it's a regular ordinal, but it is not a limit of regular ordinal. All of 0 is countable, represents a countable infinity. So I was a bit confused here. All right, so we get models and consistency here. I'm gonna gloss over that real quick. Oh, this is interesting. Now we're getting into like, what's the next level abstraction, right? Alpha inaccessible cardinals and hyper inaccessible cardinals. The term alpha inaccessible cardinal is ambiguous and different authors use inequivalent definitions. One definition is that the cardinal kappa is called an alpha inaccessible for any ordinal alpha if kappa is inaccessible and for every ordinal beta less than alpha. This is nonsense. The term hyper inaccessible is ambiguous and has at least 3 incompatible meanings. Many authors use it to mean a regular limit of strongly inaccessible cardinals, called a 1 inaccessible. I guess a 0 inaccessible would be same as a strongly inaccessible cardinal here, and then the 1 inaccessible would be a regular limit of those, and then a 2 inaccessible would be a regular limit of 1 inaccessible, and a 3 inaccessible would be a regular limit of 2 inaccessible. Other authors use it to mean that kappa is kappa inaccessible can never be kappa plus 1 inaccessible. It's occasionally used to mean hollow cardinal. I don't know what that certain kind of large cardinal number. Okay. The term alpha hyper inaccessible is also ambiguous. So there's not really a consensus what the layers are called, I guess, which is kind of funny. We made it from 0 to large cardinal in 3 clicks. Next time we can talk about what is a large cardinal. We could talk about Gödel's incompleteness theorem. We could also talk about what a regular cardinal is, what that means. And that's where today's Wikipedia Roulette ends. We started at 0, followed it to 0 morphism, wandered through the category of sets, and somehow wound up at inaccessible cardinals. From absolute nothingness all the way to the unreachable heights of infinity. Now it's your turn to steal the next episode. I pulled 3 links from the page we ended on. You can vote for which one we'll chase next in the YouTube poll linked in the description. The choices are regular cardinal, stability among infinities, Gödel's second incompleteness theorem, where mathematics meets its own limits, large cardinal, the giants that tower over set theory itself. Also, let me know in the comments which of the topics we touched on today was your favorite, and which ones you'd like to see me expand into full standalone episodes later on. Cast your vote in the poll, share your thoughts below, and if you enjoyed this mathematical detail, hit like, subscribe, share it with someone who loves seeing how fast math can spiral from simple to cosmic. I'm Rowan McKee, thanks for watching, and I'll see you in the next one.